Hey, let's talk about logarithmic functions today. Okay, we know that 2 to the third power is 8. But what's the value of y when 2 to the y power is 6? That's a little bit more difficult, okay? Now, we do know that 6 is somewhere between 2 to the second power and 2 to the third power, because 2 to the second power is 4, 2 to the third power is 8. Okay? But how do we find an exact value? This was why logarithms were defined. Okay? So what's a logarithm? We're going to let a and x be positive numbers where a cannot be equal to 1. The logarithm of x with base a is denoted by, this is red, log base a of x equals y if and only if a to the y power equals x. Okay, these two equations are the same thing. They just solve for different things. Okay, this one solves for x, this one solves for y. So again, you read this as log base a of x equals y. Okay? And the function f of x equals log base a of x is called a logarithmic function with base a. This is your base right here. Okay, now, the definition tells you that the equations, the log base a of x equals y and a to the y power is x, are the same thing. This is an important thing to always go back to. If you get lost, okay, if you get mixed up, if you get confused, you can always go back to this basic thing right here, that logs are exponents. Okay? Logs are exponents. So if you look here, this is a log, so this is a log because they're equal, right? So here's your log. It's the exponent over here. That's all it is. Logs are exponents. Okay. So, for example, the log base 2 of 16 equals 4 implies 2 to the fourth power equals 16. So here's what you know. This is your base. This is your base. This is your exponent. This is your exponent. This is your other number here. Okay? So, there's your base. Okay. Here's your exponent. And then this is your other number that goes together right here. Okay. So, log base 3 of 1 equals 0 implies 3 to the 0 power is 1. Okay, now what I want you to do is I want you to pause the video here, and I want you to take these three and rewrite them as exponential statements like this. Okay? So pause the video, go ahead and write those, and then jump back on and I'll do them for you. Okay, so here's my base. Here's my base. There's my exponent. That goes there. There's my other number. Goes right there. 10 to the first power is 10. That's true. Okay. There's my base. There's my exponent. That equals that number, 0.1. So, yes, 10 to the negative 1 power is 1/10. So back to our original question that we said, hey, 2 to what power equals 6? Well, there's my base. There's my exponent. And notice there's approximately equal to because this is an irrational number. There you go. 2 to the 2.585 power is 6. So if you want to evaluate something like log base 3 of 9, ask yourself, okay, because remember this is, if I'm going to evaluate it, it's this, right? What is that? Well, 3 to what power equals 9? And you can look at that and go, hey, that's 2. That's easy to do. X has to be 2. So the log base 3 of 9 is 2. Okay, you're going to get to evaluate these. So I'll do the first one for you, you do the last three. So let's get a new color. Getting bored with these other ones. All right, let's try this. So remember, this is an x here. I want to know what x is. So this is my base. That's my exponent. That equals that number right there. 4 to what power equals 16? 2. X equals 2. Okay, go ahead and pause the video, figure out these other three, and then we'll look at them together. Okay, so I always like to fill in the x here. 5 to the x power equals 1. Oh, hey, I know that every number to the 0 power is 1, so x must be 0. Okay, if I put in my x here, 4 to the x power is 2. Oh, how did that get smaller? Well, because I know that the square root of 4 is 2, and the square root is the same thing as the 1/2 power. So x is 1/2. Okay, on this one, 3 to some power is -1. Well, let's see. If I take this to a positive power, 3 to the first power is 3, 3 to the second power is 9. That's getting bigger. 3 to the 0 power is 1. 3 to the -1 power is 1/3. If I put a negative number in here, I get a positive fraction. There is no time ever that 3 to the x power is -1, so we would say there is no real solution to this. Okay, a logarithm like that cannot be negative. Okay, hopefully you got those three right. Okay, special logarithmic values that you should know. Let a and x be positive real numbers such that a is not equal to 1. The log base a of 1 is always 0. And that's because a to the 0 is always 1. Okay, base exponent equals that. The log base a of a is always 1 because a to the first power is a. This is one these two are pretty obvious to most people. This one kind of throws people a little bit, but it makes sense. I mean, the log base a of a to the x is x. Why? Well, a to the x power is a to the x power. Boom, done. Easy. Okay, a log with a base of 10, so log base 10 of x is called a common log and is usually written as just log. So when you see something like this, log of 100, that means log base 10. On your calculator, there are two logs, okay? LOG right here and LN. This is the natural log. We'll talk about that later. LOG is the log base 10, okay? So there's an infinite number of logs. You have log base 2, log base 4, log base 5, log base 0.2. You can do all kinds of stuff, okay? Now, for a lot of calculators, until recently, the calculators only had log base 10 and natural log on it, okay? They did not have the other logs on there, and so if you wanted the other logs, you had to use something called the change of base formula, okay? And this is the change of base formula. You should know this. The log base a of x is equal to the log base 10 of x divided by the log base 10 of a. And in fact, you can put any logs in here. You could do log base 2 of x over log base 2 of a, and it's going to give you the same answer, okay? It doesn't have to be log base 10. So it's always, this number is always written in a bigger font than this one is, so you always think of it as it's the bigger number over the smaller number, because the subscripts are usually the smaller numbers. Now that doesn't mean it's actually smaller. You could have the log base 20 of 4. This would still be bigger number would still go on top because it's written as a larger number, okay? But this comes in really handy. Now the new calculators, you don't have to do this. So what do you do with the new calculators? If you go to Math on the TI-84 and you arrow down to A, it has this key that says log base, like this. And you just hit enter on that, and it will actually do this. It'll print out log, and it'll have a little square right here, and then it'll have parentheses and a bigger square right here like this. And it'll start you out in the little one, and you just put whatever log is. So if you want log base, let's say we wanted the log base 2 of, how about 32? Okay, so you just put 2 in there, and then you use the arrow key to arrow, and it moves you, so it puts the 2 in here, and then the arrow moves you over here, then you'd put 32 in there, and then you'd arrow out, so it's going to put the 32 in there, and then you just hit enter, and it says 5. That's a lot easier than doing the change of base formula, but you could do it. So if I did it that way, I'd push my log key, LOG key, of 32, close the parentheses, divided by, hit the log key again, put a 2 in there, close the parentheses again, hit enter, and I get 5 again. Okay? So pretty cool formula, very handy. Okay, what do I got going here? Okay, so evaluate log base 2 of 6 using a calculator and the change of base formula. So you're going to do this twice. Okay, so let's pause the video and then go ahead and do these. Okay, so this first one, what I'm going to do is I'm going to hit Math. And then I'm going to arrow down to A. It's going to say log base. Okay, I'm going to hit enter. I'm going to put in 2. And then I'm going to arrow to the right. And then I'm going to hit 6. And it's actually what it's going to show me on my calculator. It's going to do this. It's going to say log square bigger square. Okay, so I'm going to put a 2 down here. And then in here I'm going to put my 6. And I'm going to hit enter. And I'm going to get 2.585. Now, this should be approximately equal to, because again, this is an irrational number. I can't really write it down. Okay, but that's close enough. Now, if I'm going to do it the other way, change a base formula, I'm going to go log of 6 divided by log of 2, like this. Okay, log 6, close the parentheses, divided by log, whoops, log 2, close the parentheses, and I get 2.585. Okay, approximately. Okay, so here's the directions for how to put that in a TI-84 in case you need to do that. I'm not going to go through that again. Okay, sketching a graph of a log equation. So here's the deal. A log equation, oops, and this is this is a typo. This should say log base 2 of x. Okay. The log equation is the inverse of a power equation. They cancel each other out. Okay? It's like 2x and 1/2 x. They cancel each other out. Adding 4 and subtracting 4, they cancel each other out. Now remember that an inverse, if you graph the line y equals x and you graph a function and its inverse, they will be mirror images of each other, and this is your mirror, y equals x. So here's 2 to the x power. Here's log base 2 of x. It's a mirror image. All right, so, if you had to graph one, say you didn't have your calculator, you didn't have to graph one, and you couldn't remember how to graph a log equation, you could always graph the power equation, then kind of dot in the mirror there, and then sketch in the other one. Okay, so like 0, 1 is going to become 1, 0. And 1, 2 is going to become 2, 1. And your asymptote, you're going to have a horizontal asymptote here for this equation. You're going to have a vertical asymptote for this one. So it has a horizontal one at 0, it's going to have a vertical one at 0. And remember that an asymptote is a line that it approaches as close as you want, but it never actually gets there. Okay. What do I got here? Oh, okay. Use a table to graph the log equation, y equals log base 3 of x. Okay. So, a lot of people, they have a really hard time with this. Okay, remember logs are exponents, so this really means 3 to the y equals x. Okay, so what you could do, if you wanted to make a table, is usually we plug x's into the table and figure out the y's. You could plug the y's into the table and figure out the x's really easy. So if I plugged in 0 for y, this would be 3 to the 0 power would be 1. That's going to be on my graph. If I plug in 1 for y, 3 to the first power is going to be 3. 2 is going to be 9. Then it's going to go off the graph. So I'm going to go the other way. Negative 1, 3 to the negative 1 would be 1/3. 3 to the negative 2 would be 1/9. You can tell it's going to approach 0. So this thing, I just graphed the points. There's 1, 0, and there's 3, 1, and 9, 2, and then it's going to be 1/3. It's going to approach the x or the y-axis here, so it's going to look like this. Oh, I missed. How horrible. Horrible and embarrassing. Now, the other thing is lots of times people think that this levels off and has an asymptote. It doesn't. It will get as big as you want, but it takes a really long time to become a big number. Okay? Because you're dealing with powers. This will get to be 1,000,000 if you want, but it takes a really long time to get there. Okay. The slope of a beach depends on the size of sand particles. If the sand is very coarse, the beach will be steeper than if the sand is fine. The slope S of a beach is related to the average diameter d in millimeters of the sand particles on the beach by the model S equals 0.159 plus 0.118 log base 10 of d. Find the slope of the beach if the average diameter is 0.25. Okay, so we live close to the beach here. If you went down to Seaside and you look at the beach, and you look at the sand is very, very tiny. You look at the beach and it's very, very flat. Okay, if you had now, if you go to the south end of Seaside's beach, the beach kind of comes in real flat and then it goes very steep. And those are big rocks that are there. Big diameter, very steep down. Okay, then it hits the sand and it's very flat. Okay, so the bigger the rocks on the beach, the steeper that it should be. Okay, and then we have, if it's 4 millimeters, that's considered a pebble. 2 millimeters is a granule. 1 is very coarse sand. 0.5 is coarse sand. 0.25 millimeters is medium sand. 0.125 is fine sand, and 0.0625 is very fine sand. So here we've got the diameter is 0.25, so S is going to equal 0.159 plus 0.118 log base 10 of 0.25. Okay, so this is pretty easy to do. Get out my handy dandy TI-84 plus C Silver Edition graphing calculator or a reasonable facsimile thereof. And I'm going to start with the log. I'm just going to push the log key, 0.25, close the parentheses. Okay, and then I'm going to take that number times 0.118 That's a negative number, okay, plus 0.159. And this comes out to be 0.087956. Okay? Very, very tiny radius. Okay, so if I look over here, that's a little bit more than this and not quite this. So we would say that that's probably very fine sand. It's going to be a very flat beach. Okay? Piece of cake. All right, there is your assignment. Have fun with that. Talk to you later.